And there we go.
Thanks a lot, Nathaniel. Thanks for inviting me to talk here and for organizing this seminar. Yeah, feel free to interrupt me with questions either via chat or just unmute yourself if there is any question. So I'll be talking about this work on verification under causally consistent shared memory. And just to see what kind of problem, what kind of problem we try to answer. So this is the simple natural safety verification problem. So of concurrent programs. So we have concurrent programs that look roughly like this, for example, two threads accessing shared memory, and we have these assertions, and we want to verify that these assertions never fail. In this particular case, for these two assertions not to fail, what we need is that these two boxes are critical sections, so they are not running together. And if we analyze this particular example, it's easy to see that everything should be okay, because if this thread runs first here, then this thread will wait in this busy loop and will not enter the critical section until this thread exits here. And then this thread can run its own commands. And similarly, if this runs first, then this will wait here until this runs and sets y to 0. So taking a bit more general view, this is a kind of a simple problem. We can express everything as a finite state machine. So this is the part that represents the program, and this represents the memory. And here we have two threads. So each of these automaton represents a thread. So the labels are the shared memory accesses. So this thread first does writes 1 to x, and then it is waiting here until it can read 0 from y, and goes on. And this red state is the assertion, denotes the assertion violation. And this is symmetric for the second thread. And we take the interleaving of these two automata, meaning at each step, either of them takes a step in this in the product of these two machines. Now, for this to be correct, we need to synchronize it with what the memory allows. And this is how we can represent the memory, assuming finite state programs, so namely a finite number of variables and finite number of values, in this case, just 0 and 1. So each state here corresponds to some mapping from locations, from variables to values. And when you read, you can read the values that are in this mapping. And when you write, you move to a different state that corresponds to the corresponding mapping. So this is again all finite, and it's quite simple. So if the program is finite, everything is decidable, and we get this problem would be p-space complete, this verification problem. We'll check if in this machine, that is interleaving of these two threads with intersection of this machine, we can reach one of the states that corresponds to the states. So in this analysis, we assumed a simple model of the memory called sequential consistency, SC for short. And if you don't know anything about weak memory models, perhaps this is what you have in mind. The memory is this mapping from variables to values, and the different threads take turns communicating with the memory. But what we get here in reality is that we have a bottleneck. So the connection with the memory and the memory itself is too expensive, and actually current machines, no existing hardware, real hardware, actually implements this model. To improve performance, they have various optimization, and shared memory implementations will provide us weaker semantics. And you can get a lot of intuition, especially for this talk, by thinking about a similar situation that happens in distributed data stores. So if I have a data store that is distributed in several places in the world, if I want to get sequential consistency, what corresponds with this kind of model, I'll need to do consensus after every step. I'll need to make sure all the replicas agree all the time. And this would be very expensive. So we settle with weaker guarantees with more and more efficient and more scalable implementations. So you can think in these terms, you can think in these terms, whatever you are more used to, but both give good intuition for this talk. So weaker memory models, there are many of them, and weaker than sequential consistency. I just list some, and some results that are already known. So one of the most well-studied one and common ones, so x86 TSO, this is the model behind Intel machines. And the decidability of the verification problem for this model was shown to be decidable. This is one of the first papers in this field in Popel 10. And more recently, they had a nicer proof, I would say, for the same result was presented in Concours. There are other models. I don't write here all the results that exist. One notable thing is that for the C++11 model, so this is another weak memory model in the level of the programming language. So it's more abstract. It has to be it can be compiled to each of these. And this model leads to undecidable verification question. And in fact, even a fragment of this model, the fragment known as release acquire fragment, which will show up very soon in the rest of the talk. It's one variant of causal consistency. And this is what when you get, if you write a C program and you annotate all your accesses with memory order release and memory order acquire, you get release acquire programs, and these will lead to undecidable verification problems. So this appeared very recently in PLDI. And there are more models, not so many results like that. What we are interested in this work was this question for causal consistency. So what is causal consistency? It's a model weaker than x86 TSO and weaker than sequential consistency. So strictly weaker. There are behaviors that this model allows, and they are not allowed by any of these. And this is a classical model, one of the old ones originated from replicated data stores. Again, these data stores that are distributed between several places in the world. And to get some intuition, just rough intuition, soon I'll show you the formal definition, but the idea is that there is no one sequence that all the thread agrees on. There will be a consensus only on the order of what is called causally related operations. I'll give a more direct definition, formal definition soon. So we give up on this one history that all the threads agree. And this model is relatively simple and still intuitive, I would say, and I'll try to show you how it is designed. There's nothing ad hoc. I think it's very natural constraint that you will all see soon. And it allows more scalable implementations than sequential consistency. So it's easier to get efficient implementations of causal consistency than of sequential consistency. Now, if we look back on this safety verification question, then what happens here is that under causal consistency, there is no causal order between this write and this write. So it can happen that this reads 0 and this reads 0 at the same execution, and both threads enter the critical section and reach assertion violation. So what was correct under sequential consistency is not anymore correct under causal consistency. Is this a problem? So, of course, it may be a problem. What I showed before is a simplification of what is known as Decker's algorithm from critical section. And Decker's algorithm fails under causal consistency. And when I saw this, I was asking myself, so how come airplanes don't crash? I mean, if we designed our programs for one memory model and it actually works in weaker memory model, this looks bad. And there are two answers. So first, there are ways to demand sequential consistency when we actually need it. So we can put some barriers in the code that will give us sequential consistency, not causal consistency, let's say. But the more interesting answer is here, the second bullet, I think, is that it turns out that it's not so easy to find algorithms that actually exploit sequential consistency in its full power. Decker's algorithm is one of the few examples I know, but we often don't need full sequential consistency. And moreover, I want to say that often causal consistency suffices for correctness of algorithm, but this is something empirical that I'm not going to justify more than just saying it. And maybe for this audience, it's clear what we need is, of course, to have formal, simple, clear semantics that we can work on before we do the verification. So turning to causal consistency, and again, interrupt me if there are any questions at any point. Causal consistency is meant to support this kind of what I call flag-based synchronization. Let's look at this program. So we have two global variables, x and y, initially both are 0. The first thread is setting y to be 1 and then x to be 1. And the second thread is reading x and then it reads y. And the question, can we get 1 for x and later 0 for y? And the answer that under causal consistency, just like sequential consistency, we are not allowed to get this behavior. And this is important in concurrent programming. It's a useful idiom. So one thread can initialize some data structure. This will be this write, and then set some flag. The other thread will see the flag. It should be able after that to use freely, safely, the data structure and not to get some uninitialized value. So causal consistency, I believe, is useful because it supports this idiom, namely it doesn't allow this behavior. Let's see how it works. So it's not defined using a machine. It's not a standard operational semantics with machine and buffer and things like that. It's going to be a declarative definition using execution graphs. So if we want to analyze if this behavior is allowed or not, we have to draw an execution graph. So that's a directed graph. The nodes, we call them events. They are for each shared memory access. So this is the initialization of y to be 0, write y 0, then write x 0 in this side in parallel. And then after that, the first thread writes y to be 1, and then writes x to be 1, just like the program says. And the second thread reads x 1 from x and reads 0 from y. And again, this is because I'm particularly interested in whether this behavior, reading first 1 and then 0, whether this is allowed or not. So I'm drawing this graph, and the arrows, we call them program order. So this comes from the syntax of the program, initialization before everything, and then every thread according to the syntax. And then the model says the first condition, so this is all models say this, that every read has to be justified. So if I have here a read of 0 from y, I need to justify it with some event in the graph, some node in the graph that writes 0 to y. In this case, I have only one option. I can only justify this read from here, and this read can only be justified from here. We call this justification RF, reads from relation, and this is the first requirement. We need to have this kind of relation. Then the model defines happens before, which is simply you take the transitive closure of the union of program order and the reads from relation. So all the paths that you have in this graph, this is a partial, it should be a partial order. The constraints on happens before, to check whether execution is allowed or not, we need to meet these constraints. And what are the constraints? So first, we require that indeed it is a partial order. There should not be any loops, any cycles in happens before, and this is all fine in this execution. This is a partial order, the union of the two arrows. And the second condition, this is what fails here, this pattern should never appear. And I think this pattern is very intuitive. If you need to come up with some pattern, this is the one you will disallow. Let's see what happens here. So we have a read, and it reads from some write to x, to some variable x. But there is this intervening write, and this write, the read is aware of this write. Namely, we have an happens before from this write to this read. It's another write to x. But this write is also after in happens before this write to x. So we'll say that the read is already aware of this write, and this write is later than this write. So this should not be allowed. It should not be read from here. It should at least read from here. So this is the pattern that is disallowed, and this is what is violated in this graph. So we have this read of y that reads from here, but there is this other write, happens before via this edge, and it is in between because there is also happens before like that, 1, 2, 3. So we are not allowed to read 0 here, we have to read 1. So this is the whole model of causal consistency. And this graph will be inconsistent. We'll say that the program outcome is disallowed after we've done this analysis. If we look back on the original program, I'll do it quickly, then we see that nothing forbids the behavior that reads 0 and 0, that leads us to the assertion violation, simply because when I'm reading, for example, 0 here, I don't know anything about this write. Again, think of this as happening in 2 different places in the world. So there is no path from here to here. I don't know about this one, so I can read 0. Nothing is violated, and this graph is consistent according to the previous definition.
Sorry, just a quick question. Umang is asking, is this the RA fragment of C11?
Not yet. One second. A few slides. I'll answer. Thanks for the question. It's a bit weaker than RA, but bear with me a few more slides. Another example, and this is when I said it is weaker than x86 TSO, This is because causal consistency is non-multi-copy atomic. And what we mean is that different threads can observe writes in different orders. And this is the classical example. We have 4 threads. One thread is writing 1 to X. And the last thread here is writing 1 to Y. This thread sees X is 1, but Y 0. So from the point of view of this thread, this write was before this write. And from the point of view of this thread, this write was after this write. So they have different views of how the writes were performed. And if we analyze this with the graphs, we see that nothing here again is everything is okay. For example, when I'm reading 0 from X, there is no, I don't know about this write. There is no path from this write to this thread. So again, it's allowed. And if you know the x86 TSO model, so this is not, it's not allowed there. So we have a weaker model. You can show that this is a weaker model than x86 TSO. Now the question, and this is related to Umang's question, what about concurrent writes? Well, from what I said so far, it leads to very strange behavior, I would say, because if we have the first thread here that writes 1 to X, and the last thread writes 2 to X, in the middle we have a thread that reads X, and it's all fine to completely oscillate any way we want between these values 1 and 2. So we first read 1 and then 2 and then 1 again. This would be the graph. And the reason is simple. Why is this okay from what I said so far? Because there is no happens before between this write and this write in any direction. So the writes are not ordered, nothing will make them ordered, and then I will never get the evaluation, I'll never get this bad pattern that I mentioned before. So again, this will be allowed. Now, is this a problem? Depends. There are several options what to do about that. And this is where there is not just one causal consistency model, there are several of them, at least 3 that I consider in this work. So let's talk a bit about them and see the differences. But this is all about this question of concurrent writes. So what can we do about it? One thing is to do nothing. Just have what I said so far and allow this oscillation 1, 2, 1, 2, 1, 2. We don't care. Maybe the algorithms we have work well also with this oscillation. They don't care that this may happen, even though it looks maybe strange from a sequential consistency point of view. This will lead us to what I call weak release acquire, WRA model. Now, the other option is to make sure that the writes are ordered. By that, for that, we need a different order, not just happens before, we need another order. I'll soon next slide will show exactly how. And there are 2 ways how to do that. One of them will lead to release acquire model. This is the C11 fragment, the one that C chose to go for. And the other is stronger, is called strong release acquire. Let's see what are these options exactly. These 3 variants. So again, weak release acquire is simply what I said so far, nothing else. We just keep this and ignore what concurrent writes. And the 2 others require another relation. They will say that there should also exist for consistency. This is an existential quantifier. There should also exist a total order on the writes to the same variable. We call it a modification order, that we will use it instead of happens before to decide on whether a write is later than another write. So this will be a total order on the writes to every location. So we will always be able to see which one is after which, and we will not use happens before for this. So we take the same pattern, but we replace this by modification order. Now we still need, in order for this model to be stronger, as I claimed, than this model, we still need modification order to match happens before. And there are 2 ways to interpret what it means. One of them is the release acquire option. It will simply say happens before cannot contradict modification order. So if happens before says that we go this way, then modification order, this existentially quantified relation, has to go also in the same way. And this will give you release acquire of C11. That was the question from before. Another option is to say that we don't allow any kind of cycles in modification order and happens before. And this can be a modification order on variable X, then this can be on variable Y, so these are not the same variable necessarily. And I call this global agreement between modification order and happens before, and this would be local agreement. And these are 3 choices will lead you to different variants of causal consistency in different strengths. So quickly, let's see if we now analyze this in release acquire. If without loss of generality, we have modification order from here to here, then this thread now cannot read one under release acquire because it is already aware via this path of this other write that is later than this write, even though there is no happens before, because we use modification order to check for which write is overwriting which write. So this shows that weak array, W array, is strictly weaker than array. There are examples that I'll skip because they are a bit more complicated, showing that release acquire is strictly weaker than strong release acquire. This is again not the same model, and we have these three variants. So the picture looks roughly like this from the fragments I'm considering. So we have causal consistency. We have three different options. This release acquire in the middle, the one that was shown to lead to undecidable verification problem, is the one that C and C++ 2011 chose to go to and recently to use and read for causal consistency. And recently also Java 9 is using this. You can go to a stronger model called SRA. And in fact, I saw that in distributed data stores, when they say causal consistency, again, there are many variants also there, but usually, very often, what they mean is what we call SRA. So I think the most standard distributed data stores causal consistency notion is not array, rather it is SRA. One other thing that we showed in this paper from Propel 16 is that SRA completely captures causal consistency in the power architecture. So IBM's architecture, and it doesn't give you causal consistency, but if you use certain barriers, you will get causal consistency. And the kind of causal consistency you will get is exactly SRA, is not array. And now you can also go weaker. And this was also a well-studied model. So in this paper, when they say causal consistency, they mean weak array. And in this paper, what we did is we tried to do, in some part of this paper, we tried to do verification for weak array. It looks promising because since we don't have this existential quantifier or modification order, we can do bounded model checking, perhaps in some cases more efficiently than what we do here, but there are some trade-offs that I'll not discuss in this talk, which is not about a bounded model checking problem. Okay, but to be completely honest, this is a nice theoretical distinction, but in practice, it has a limited significance because of this theorem. We can show that if a program doesn't have write-write races, so if we don't have concurrent writes to the same location, then the behaviors of this program under weak array and array and SRA, they all coincide. So these distinctions are only important for programs that use concurrent writes. And there is one nice thing here is that you can check for data race for WW races, write-write races under the strong model. You don't need to check to understand the weak model in order to check for the existence of these races. And many programs don't have write-write races. And this distinction is not important at all. So what we proved that the verification problems under SRA and WRA are decidable. And this is in contrast with release acquire array. So it's nice. I think we managed to surround RA, the undecidable one, with the decidable one above and the decidable one below. And to do that, we developed a new semantics for these two models, SRA and WRA. And I think that actually the new semantics, I find it more interesting than the decidability result per se. I believe it will be useful also for other verification questions and not just the decidability. As a corollary, of course, we obtained that if we don't have write-write races, then also RA is decidable. This, if you're particularly interested in verification of C11 programs written in the release acquire fragment, then you can use this theory, corollary on this theorem. So in the rest of the talk, I'll describe how we showed this first theorem. Any questions so far? Okay. So the first observation is that it is not going to be an easy problem from a complexity point of view. For all these causal consistency models, this verification problem is going to have non-primitive recursive complexity. And the idea is that it's not difficult to show that one can simulate a lossy FIFO channel machine using causal memory. It's exactly the same reduction that appeared for x86 TSO in this paper. Essentially, one uses the the memory to simulate the channel, and things just work, and without any difference between TSO and causal consistency. In particular, there aren't any right traces in this reduction. So this is very similar. It just gives us a kind of very hard lower bound for the complexity. So one negative side. On the positive side, let's now think how we do prove decidability given this complexity bound. So for decidability, one of the things we'd like to do is to think about these machines as machines, as given operational semantics, not just as declarative semantics. We're used to think in operational terms to prove such decidability results. And it's not so difficult. We're just changing a bit the point of view. So the idea, there is some animation here, the idea will be to think about this graph as the state of the memory in our system. So the history is the state. Instead of a mapping from locations, from variables to values, we keep the whole history as our state. And every step of the machine, so for example, thread 1 writes 1 to X, it will require that an event is added to the graph in a way that keeps the graph consistent. Now the second step could be that thread 1 reads 0 from Y, so we add this read, we need to justify it, we justify it, everything is consistent, we go on. So we can look at this declarative semantics that I mentioned as if it is an operational machine working with this kind of, this is our state, the part of the state of the memory. And the reason it works is because consistency is prefix closed, and we can require consistency at every step. We don't need to wait all the way to the end to check for consistency. Okay, with this thing, what makes this problem still very difficult is that even if the program is finite state, when we look at this as a state machine, it's infinite state, because the graphs can be unboundedly large. The programs may have loops, and it can grow and grow and grow, and we will have infinite number of consistent graphs as our states. So we reach an operational semantics, which is perhaps strange in the first look, but is, I think, normal operational semantics, just infinite state. Now, to establish decidability, we would like to use the framework of a well-structured transition system, which allows us to prove decidability of such reachability questions in infinite state systems. And the challenge now reduces to how to express causally consistent memory as a well-structured transition system. So I'm not sure if I want to assume, and can assume that everyone knows well-structured transition system. Let me very quickly introduce it. So this one way to look at it is to start from this backward reachability algorithms and to understand it from there. So we have this is the simple backward reachability algorithm. We have a labeled transition system. We ask if this state, some state Q bad is reachable. What we do, we initialize a set S to include this bad state. And then we do this fixed point calculation. So we increase S with all the predecessors of S using the reachability in the one step of the LTS. And we continue until we don't change S anymore, until we reach a fixed point. In the end, in the set S, what we have is the set of all states that can reach Q bad. And we ask if some initial state is included in this set or not. Now, to make this thing, since this label transition system is infinite, to make this work, we need a way to actually represent these infinite sets, made possibly infinite sets, and in a way to guarantee termination. And this is what well-structured transition systems are doing for us. So the idea is to equip the system with some well quasi-order, and then we will use as a set S, we will use upwards closed sets of states. So a state that is upwards closed can be represented by the set of minimal elements, a finite set of, this is a finite basis, a set of minimal elements in this order. So we will use this to represent infinite sets, and this also guarantees termination. And why it is working, what makes this analysis precise is we will have this condition that requires the quasi-order to match the transition system. And this condition says that if Q1 can take a step to some state Q2, and Q1 prime is larger in the order than Q1, there should exist some state Q2 prime and that is larger or equal to Q2, and Q1 prime can reach in some sequence of steps this Q2 prime. With this condition, we can show that the algorithm that from the previous slide is indeed precise and is not losing any, when working with this representation, is not losing any precision. Now, one simple observation is that instead of compatibility, we can get it for free if we have this step in our system. If we have this, what I call lose step, so Q prime, if Q prime is larger than Q, then we allow the transition from Q prime to Q, and then it's not difficult to see that we get this for free. So we would like to have this kind of step in our system. So we need to find a well quasi-order and to have this step in order to have a well-structured transition system. When we have this step, we'll call the system lossy, and this reduces the challenge to characterize causal consistent memory as a lossy system. Maybe that was too quick, but I hope some of you know the well-structured transition system, most of you from before. If not, just keep in mind that we want to have this step in our system, and this will give us decidability. So, question? If we try to do this for causal consistency naively, there are some critical obstacles that make this seem it is never going to work. The natural thing would be to try to think about embedding of one partial order in another as an order, but there are two critical obstacles here. First, partial order embedding is not even a well quasi-order, so we are stuck already there. And even worse, if we just lose something, we lose some event from the graph, let's say we lose this event, then we allow more freedom in the system. So here, after this point, this thread cannot read x0, but if I just remove this one, now this thread can read 0 from x. So these histories are not lossy. In a sense, if you lose some information, you allow more behaviors. And how to make this work, I think difficult. I was thinking about this for quite some time. And the breakthrough, I would say, came from some doubt I had, and later I found this as a philosophical, psychological, let me correct, doubt in some forum. So this is the question that I saw. Why do I keep focusing on the past instead of the future? And this is the main idea, main takeaway of this talk, I would say. The idea would be, instead of keeping in the state the history, what was already done, I want to keep in my state what is the possible future of this particular state. And why this is good intuitively is because futures are lossy. If I remove something from my future, I just restrict the freedom that I have in my system. I'm not allowing more transitions that were not there before. This is in contrast to what happens if I lose something from the history. So what we do for S array in a bit more details is that, and I'm specific for S array here for first, later I'll maybe say a few words about W array, but we will record in the state what we call the potential of the thread. And this is the answering the question, what possible sequences of reads each thread can execute. This will be in the state of the system. As an illustration, so this is just one thread, let's say. It has the potential to first read 2 from X in this state, then read 2 from Y, then read 0 from X, then 0 from Y. Then, for example, it can read 2 from X and consume this thing from the potential, and now it has a smaller potential, and go and so on another step. There is also a lose step in the semantics, this epsilon step. You can non-deterministically simply lose things from the potential, and then let's say the thread can finish its potential by reading 0 from Y. So as a first approximation, this is how our memory is going to look like. The states will be mappings from thread identifiers to these potentials. These are sequences of this form. This R is just a marker, read, X, V, X is a variable, and V is a value, and finite sequences of these elements. Initially, we assume that everything is 0. So we'll have this mapping that maps only to the value 0. And the well quasi-order we're going to use will be per thread subsequence. So for one state is smaller than another, if for all threads, the potential of the thread in state Q is a subsequence of the potential of the thread in state Q prime. And this is easy to see that this is well quasi-order. How it works in this example, let's see. So this is initially, this thread has the potential to read 0 from y and 0 from x. Then it writes 1 to x. It puts in the potential, let's say, in the other thread, the option to later read 1 from x. And then it writes 1 to y. It puts this, the second thread writes 1 to y. It puts this in the potential. But then the first thread can consume the first option from its own potential. And later the second thread can consume the first option from its own potential, and so on until we reach the error state. So another illustration of how this is going to work. A few more details, I need to define how we do this potential maintenance, how the steps of the system look like. So we have a lose step, I already talked about that. We have a read step, and again, with a precondition, in order for thread tau to read v from x, we need that the first element in the tau's potential would be indeed of this form, Rxv. And the right step is the most interesting step. This is where we pushed all the complexity to the right step. First, there is a technical condition related to strong release acquired, that when you do a write of value v to location x, there is a precondition that there shouldn't be any read x options in the potential of the writing thread. This is because under strong release acquire, when I'm doing a write, I become aware to the most recent write in the whole system. So I shouldn't be able to read earlier writes later in my potential. But the more interesting thing is what happens in other potentials. I should place these new options, Rxv, in the potentials of the other threads. And the question is, where should I do that? And these are examples showing that this is a delicate question. So let's see. In this case here, this thread writes x1, and this thread is here. It didn't perform anything. And it wants later, it wants to read 1 from x and 0 from y. And this is certainly should be allowed. It is allowed also under sequential consistency. So the second thread has the potential to read 0 from y, in this case, we are just before executing this write. And now the first thread wants to execute its own write and to put this new read option in the potential of the second thread, but above this existing option. And this should be allowed in order to get this behavior. On the other hand, if the second example here, the first thread already wrote y to be 1. The second thread again has the option to read y0 in its potential. But now we don't want to allow the second thread to first read x1 from x and then 0 from y, because this is again exactly the flag-based synchronization that should be disallowed under causal consistency. So here we don't want to allow to put a new option here above this existing option. So the question, do we have enough information in our state to see where we can put these new options? And yes, we do, and this is related to the potential of the writer that is different in these two examples. And we call this the shared memory causality principle, and you can think about it as a potential characterization of what is causal consistency. It's a long English sentence, let's try to see. So it says, every sequence of reads that a thread pi can perform after it reads from a certain write executed by thread tau. So thread tau executed some write and thread pi read from it, and now it wants to perform a sequence of reads. This sequence could be performed by thread tau immediately after it executed the write. The idea is that thread pi is now, after it reads from tau, it is synchronized with tau. It knows everything that tau knows about. So whatever pi can perform, tau should be able to perform immediately after it did its own write. Maybe tau is less restricted, but certainly whatever pi can do, tau can also do. This leads us to the following condition. Suppose now we have this in the potential in thread 1, and this in the potential of thread 2, and we want the first thread wants to write 1 to z. So where would it put it? It can put it in many places, but one option would be to put it here, this new option. Why? Because what we have here, this whatever the thread will do after it performs this read is indeed a subsequence, is something the thread 1 can do now when it is just writing 1 to z. So this is the condition we are going to have. You're allowed to put a read option somewhere if you meet this principle, if whatever you have below the read option is a subsequence of what the writer thread could do just when it's performing the write. And we can put many of these, not just one. Of course, the second thread may want to read one from Z many times, but we need to keep maintaining these conditions. So we cannot put it here, for example, because the writer thread doesn't have the potential to read 2 from Y. That's the main idea behind the semantics, and this is what happens in this example. In this first example, the first thread has the potential to read 0 from Y when it's performing this write. This is why it is allowed to put this one here. In the second example, I just performed Y is 1. So I don't have the potential to read 0 from Y. This is because of the local conditions that I glossed over a bit. But then it means that when I'm not allowed to put this read option above this existing read option in the other thread's potential. So with this, we define the semantics. There are some more details that I don't show, but this is actually not so complicated semantics. And the details are that we need actually multiple lists per thread. So one potential is not enough. We need a finite number of them sometimes. We need to keep the identifier of the writer threads in our read options. This is because there may be cases that two threads are writing the same value to the same variable, and we don't know to distinguish. We need to know which one wrote what. And if we want to handle RMWs, I didn't talk about RMWs. These are atomic read modify writes that are important instructions to implement things like locks. And then we need some additional flags, but this is not so difficult. So we did with this, I have some examples that I'll skip why we need all these complications, but in the interest of time, I'll skip them. And I also wanted to say a few words about weak release acquire, what we do for weak release acquire. So far, I described what we do for strong release acquire. So for weak release acquire, we need to revisit this condition, that precondition in the write step, that when I'm doing a write to X, I don't have read from X in my potential. Because in weak release acquire, if I'm not aware to other writes, I should be able to keep being able to read them even if I perform my own write. And the way we handle this, I think I'll skip the examples again in the interest of time, is that we include in our potentials not just read options, but also write options. So this write X means that the thread is allowed to write to X at this point. And we have some conditions on when we can put the new read options with respect to existing write options in order to satisfy the constraints of causal consistency. But what is nice is that the causal principle works without much changes also for weak array. We just say it's not every sequence of reads, it's actually every sequence of reads or writes. Whatever you have, every sequence of operations. So it all generalizes nicely. And for example, in this case, this thread can put this new option here, but not here, because here this thread has the potential to write to X, and this thread the writer thread doesn't have the potential to write to X. So again, in the interest of time, I'm skipping most of the details here, but the slides and the paper will be available online later, and I will be happy also to discuss this in more details. So what we proved that the potential memory systems are equivalent to the SRA and array history-based systems. And this is a kind of complex proof. We have simulation proof, forward simulation in one direction, backward simulation in another direction, and we did this in Coq in order to gain more confidence. Then we proved, and this is more easy because we have the lose step explicitly, we proved that when we synchronize a program with this potential-based system, we get a well-structured transition system. And from that, we get that the verification problems are decidable. And for write trace-free programs, also for array, we have a decidable problem. A few more questions that we are currently interested in thinking about is we don't have an implementation. The complexity is very large, of course, but for small programs, this can be useful, and we don't have any implementation. There is an open question about what happens with release acquire without RMWs. So this thing with potential doesn't really work for release acquire. And this is because of the delicate interaction between modification order and happens before. On the other hand, if you look at the undecidability proof, they crucially use RNWs, these atomic read modify rights that I didn't talk about. So it's still open if RA is decidable without these, as far as I know, it is still open without these RNWs, and perhaps the potential framework would be useful for this, or maybe not. Other questions is, what about other models? Can we get closer to release acquire with different constraints and still have a potential-based system? Parameterized programs when several threads, unbounded number of threads is running the same program, is it decidable or not? And finally, I would like to use the potential-based semantics to develop things like program logics and model checking algorithms, and not just for the decidability. Yes, so this concludes my talk. I just, before finishing, wanted to mention that if you find this interesting and you're generally interested in concurrency verification, I have a ERC project and I'm looking for students and postdocs, so feel free to contact me, or if you know someone that may be interested, and refer him or her to me. And that's it. I'll be happy to take questions if there are any. Thank you.
Thanks a lot. So thank you very much. I'll stop the recording here.